Yeah, thanks for introduction, and also thanks for giving me this opportunity. So today I want to talk about independent domination of graphs with bounded maximum degree. And this is joint work with Eunkyung Jo and Mingi Kim and Sang Yeon. So you might remember Eunkyung's talk. She visited IBS about 2 months ago. So it's not that long ago. So at the time, she talked about some result about this independent domination number, and also introduced several different problems. So here we solved one problem that she talked about. Okay, so
Are you assuming prior knowledge of that talk because I wasn't here?
Sorry?
Are you assuming that we remember this talk because I wasn't here?
Yeah, don't worry. Okay, I will start from very beginning. Okay, start with so just usual domination number. So I will denote gamma object. So this is just minimum size of dominating set. And so your dominating set means, so consider vertex of set. If we consider its closest neighbor means a vertex in W or vertex connected to W. So this set contains all vertices of G. And now I will want to consider independent domination number. So I'll denote I of G. Just as similarly, minimum size of independent dominating set. And what is independent dominating set? Just independent and dominating set. So it is equivalent to maximal independent set. Okay. And obviously, yeah, maximal. Okay. Maximal. So obviously, what we can know is gamma of G is at most because independent dominating set is a dominating set, and of course, it is at most the number of vertices. So from this trivial relation, mainly what we want to do is to see the difference between these two numbers or these two numbers. So how the difference can be big. So let's see simple example. So consider complete bipartite graph with same size. k and n. Then what is the domination number here? Two, yeah. That's P. One vertex at each side. So this is 2. However, independent domination number. So here these 2 vertices are not independent. So if we choose one vertex from left side, then we cannot choose the vertex in right side. So this must be n. So here, in this example, these 2 numbers can be very big. And for this number, I of g is only about half of the whole number of vertices. So mainly, I'll focus on the relation between these 2 numbers. So question is, how large this ratio can be? So I will first introduce some known results for k-regular graph. So let's say that G is connected and k-regular. Then what is known is I of g is bounded by half of the number of vertices. And they collected when only if graph is exactly this complete bipartite graph. So because there are only one graph which achieves this bound, so people ask what happens if we forbid this graph. So if G is not this graph, then I of G is bounded by this constant times number of vertices. This was proved by Rosenfeld, and this is result by 임경조 and 일기최 and Bromback. And this bound is tight when k is either 3 or 4. This is, I think, for k lists. And we don't know whether it's tight or not from 5. And also, in the same paper by Ingyong and Ilgyu and Brom, they asked, how about the graph with bounded maximum degree? And they conjectured the following statement. So here G has no isolated vertices. And maximum degree is bounded by delta. Then IOG is bounded by some constant depend on this delta and times number of vertices. And here the constant is given by like this. Yeah. Sorry. This one is tight. And the example giving this tight one is consider clique of this size. And for each vertex on this clique, add vertices of degree 1. How many? This number. Like this. Yeah. Then each vertex on this clique has degree delta. And also similarly, this one also gives same bound. Click of this side and then one less number of if delta is odd. And I will denote this graph as the h of this size of clique plus this many vertices of degree 1. And this is here we have, let's say this graph is G. The number of vertices in this graph is, so for this many vertices, each of them is connected to this many vertices. So yeah, four vertices like this. So it's exactly this number. And then if we compute I of G, then we can only take one vertex inside of the clique, and then we have to take all the other vertices of degree 1. So that will give exactly this number. Okay. And this conjecture is trivial when delta is 0, 1, 2. And for delta equals 3 case, it is proved by variator. And they also find our graphs which satisfy the equality. So here, first case is the number of vertices is even, and she is either corona of test PM or corona of path and cycle CM. So here, corona of path means we have a path of length m, and with m vertices, and then to each vertex on this path at spike vertex, like this. And similarly, for this cycle, we can add this. For these two graphs, we can know that here independence domination number is exactly half of the number of vertices, because it's this yellow edge, we have to pick either this one or this one. So independent domination number is at least half, and we can take this set. Oh. And there are some more cases. These other K22 or K33 and some more graphs G1, G2, G3. Here G1 is this. G2. So here all of these graphs have 6 vertices and independent domination number is 3. And our result is, first of all, we prove this conjecture for all delta from floor. And we also show that when equality hold, every component of G is either this graph or this graph. So if we consider only connected graphs, then these two graphs are only the case which is satisfies the equality. No, for this conjecture, this example is only. Okay. Okay, so now our little question is, we know that there are only 2 graphs which achieve tight bound. So what happens if we forbid those 2 graphs? So can you guess which graphs will give the next optimal bound? This close. Yeah, nice guess. Actually, this better example. So consider two copies of those graphs. Like this. And we want to connect those two graphs. So take one vertex of degree 1 to each component, and then gluing them together. So like this. This graph gives the next bound. Then, sorry?
So for bit under what subgraph really?
We are only consider. Let's say we only consider connected graph.
Oh, okay.
And then if graph is not equal to both of those graphs, then the next optimal bound will be obtained by this graph. Then now you can guess which one will be next. If we forbid this graph.
We three together?
Yeah. Consider one more copy. And then, gluing similarly like this. And the way how to glue is not that important, so we might add to this vertex. That's not that important. And the important thing is we are connecting those components like a tree. So our next result is, so the optimal bound can be obtained by this graph, and the next one is by gluing those two, and the next one is adding one more, and adding one more, and so on. And we will call that this kind of graph is delta spatial. Okay, so now I will define formally this delta spatial graph. So, first of all, it's connected graph. It's called delta spatial. It is so first of all, every vertex which belongs to some cycle has degree delta. So here, this part is the vertices contained in a cycle. And also, every edge has at least one end. Its edge has at least one end should be belongs to some cycle. So if we only consider these vertices that belong to a cycle, should be independent set.
And condition 1, every vertex that belongs to some cycle.
Sorry. And the last condition is, so consider a subgraph induced by these vertices, that means contained in some cycle. Then each component is either click or some odd cycle. Can you see the bird? This component. Some cycle is this click or this click, or it can be an odd cycle only when delta equals 4. So actually, for delta equals 4, so this graph looks like this. But here we will also consider not only for triangle, consider C5 and then add 2 of each vertex. Similarly, consider any odd cycle and then also a graph by gluing them. And here, actually, a singleton vertex is also delta spatial graph. Now what we want to do is we want to prove it all delta spatial graph. Then what will be the bound? So assume that G is connected and maximum degree is bounded by delta and not delta spatial. And delta is 4. Then I of G is bounded by this bound. Actually, there's one more case. It's actually if delta is not equal to 5 and delta equals 5, then it's quite strange, but it gives different bound. That gives this number 6/11, which is less than 5 or 9. Yeah, it's very strange. And this bound is tight. And what will be? That's what Deb said. Yeah. So this one can be obtained by a graph deleting one vertex of degree 1 from any delta spatial graph. No matter how big the delta spatial graph, after deleting one vertex of degree 1, that will give this one. And also, for delta equal 5 case, if we consider this graph, then that graph will give this 6/11 bound. So that means there's another example that gives exactly this number. Can you expect which graph will give this 5/line? I mean, it's very simple. It's very simple. Consider this 4 spatial graph. Yeah, of course, this is not 5 spatial, but this graph gives this one. And we can also make infinite class of graphs which accept this 5/line. So just consider many copies of this. So consider many copies of this. And just connect them like this. Then it has maximum degree 5. And this graph will also give this 5/line bound. And I mean, the way how to connect is not that important. We can add like this edge also. I mean, this edge is not that important. The reason why that I'm adding these kind of edges is just to make a connected graph. Okay. And you also computed the exact independent domination number for delta spatial graph. Which is delta spatial. Then independent domination number is this number plus some constant. And actually this is equivalent to I of g minus 1 is this number times vertex number 9. So somehow it's very strange, but I of g is not linear by this number, but I of g minus 1 is linear by this number. So now I want to explain a proof idea. So to prove our main result, so actually we proved a bit stronger statement. So now our graph G doesn't have to be connected. And we will denote n delta of G. This is the number of delta spatial components. And then what we want to prove is I of G is bounded by some constant times number of vertices, and then T times this number of spatial components, where T is exactly corresponds to these two numbers. Yeah, because here, yeah, a singleton vertex is a delta spatial graph.
Yeah.
Yeah, because there is no edge, no cycle. So here, this theorem directly implies the above theorem. So the proof idea is quite simple. We are going to use just induction. And to use induction, we don't want to assume connectedness. We are going to delete some vertices, and also we will delete some edges. So in this statement, we didn't assume that G is connected. And actually, did I mention? Oh, I forgot to mention here that actually, Eungyung and Il-gyu and Grom, they also proved the conjecture for delta from 4 to 8. And actually, in their paper, they only write delta equal 4 case, because for the other case, they can compute, but it's very complicated, and they have to do many case studies. So, and then they gave up to prove for other deltas. And actually, our proof idea is similar to their proof idea. And here, they only use vertex deletion. But here, we also considered edge deletion. So that's the our biggest difference. So from then, now we don't need any case study. Okay. So our proof idea is just using induction on the number of vertices plus number of edges. And also we may assume that G is connected. Yeah. If not, we can, by induction, we can obtain this directly. And then also, we may assume that G is not delta spatial, because for delta spatial graphs, we already know that the equality holding. Okay, so this means n delta of G is equal to 0. So we want to show I of G is bounded by 1 minus t times n. So here also, we are going to use vertex deletion. So consider two graphs, G and G minus. For any vertex V, consider graph vector deleting V and neighbor of V. Then for this graph, if we take a independent dominating set and then add vertex V, this will give an independent dominating set of G. So that means this number is bounded by this number plus 1. So now we can use induction for this graph. Then means we obtain n minus degree of V minus 1. And then number of spatial components of this graph plus 1. And this is equal to minus t times n so this is equal to this number. So here, if this part is negative, then we are done. Yeah. So that means we may assume that this part is positive. Okay, so then this means this value is larger than this number. So we obtain some lower bound for this number. And now we are going to use edge deletion. For delta spatial case, we already computed I of G, which is exactly equal to this number.
The previous theorem.
Okay, now this is our key part. So our claim is if G has a vertex degree at least 2 with no neighbor of degree 1, then we are done. to prove this claim, then we can assume that for any vertex of degree at least 2 must has a neighbor of degree 1. And I'm not gonna prove this claim, but here we use edge deletion, and then that's our key ingredient. Then why this claim is important? So here we obtained this inequality. And actually what we want to do is we want to make sure that this number is not that big. So this claim has to compute this number. Okay, first of all, we can show that our delta spatial component of this graph is actually isolated vertices. So this one is number of isolated vertices in the graph. Okay. So to prove this, let's assume that there is non-trivial delta spatial case after deleting these vertices. So that means consider V and its neighbor, and then after deleting these vertices, we may have some non-trivial delta spatial case. We may have like this. Because V is connected graph, so that means there must be some edge connected to this part, this graph and this graph. And all the vertices in the clickwise cycle has already maximum degree, delta. So it should be like this. Then see this vertex. This vertex has degree at least 2, but it has no neighbor of degree 1. So because of this claim, this kind of things cannot happen. So we can show this. And then we want to bound this number. Okay, so that means here there can be some isolated vertices after deleting those vertices. So these vertices are isolated vertices in this graph, means the neighbor of this vertex contained in this set, like this, or like this. But these kind of things are impossible. I mean, here this vertex is connected to 2 vertices in the neighborhood. Then this vertex again has degree at least 2, but has no neighbor of degree 1. So that means it can be connected to only 1 vertex of neighborhood. So let's draw again. So this must look like this. So now I can give some bound for this number. So let's say that P1 is the maximum number of neighbors of degree 1 of a vertex. Then this number is bounded by, for each vertex here, the number of vertices here means the degree of V minus P1. Because there can be other vertices of degree 1, P1 many. For this number of vertices times P1. So this number is bounded. Because each vertex in this set can have at most T1 many neighbors of degree 1. So we obtain two inequality, this one and also this one. So by using these two inequality and by doing some calculation, we can have our main result. Okay, time is almost up. Now I will just introduce open question.
Only use the edge deletion method for proving
Claim.
claims.
Here, as you can see, delta spatial graphs have so many vertices of degree 1. So now our question is what happens if we forbid all vertices of degree 1? So we want to assume that she has a maximum degree delta and minimum degree is at least 2. Consider this case. Then what will be the optimal bound? My guess is, I don't know, but maybe we consider two delta spatial graphs. And then to each vertex of degree 1, connect them this way. So like this. So like this. So gluing them like this, then we will obtain a graph with maximum degree 2 and minimum degree 2. I think this graph might give the optimal bound. I don't know, this looks very natural. Yeah. Okay.
What's the number for this graph? What's the...
It's quite complicated, I don't remember. Yeah. I mean, my guess is if we also consider a graph with minimum degree 3, then maybe we consider 3 copies of them and then in similar way. I don't know. Okay, that's the end of my talk. Thank you for listening.
Thank you. Any questions?
So, is it possible that for every value of n, you could find the connected graph with the largest, there's a connected graph with maximum degree delta and the largest possible
independent domination number. Because you have these extremal graphs which get bigger and bigger, which are all extremal if you give the number of vertices exactly.
Yeah.
But they sort of come at these intervals of you have to add on like delta squared on like lots of new vertices. So you miss the intermediate specific values. But then you also have this result that deleting exactly one leaf, you still extreme in some sense. So I wonder if you delete 2 leaves, is it like, if you fix the number of vertices, is that still extreme?
Yeah, that
This is
might be, yeah. This makes sense, yeah. I think maybe deleting to a vertex, that might be also
But delta is 5 is different, right? Because you can have odd cycles.
Yeah.
Things, so period is gonna be 2.
Right. Yeah, I guess then maybe you get maybe even or maybe delta equals 4 when you got the other cycle, maybe that covers it. Because you can have any number of vertices in the other cycle. Or is it?
Perhaps you can say that at least it's periodic.
Oh yeah.
Some constant, maybe subtract some constant. It's constant, it's periodic.
Yeah. Do people look at this question if you don't have it, if you just have the minimum degree and not the maximum degree?
Only minimum degree.
There's some easy. So if the minimum degree is at least some value,
Yeah.
there's some
complete
but this,
points.
right. I see. Yeah, okay. Maybe that's the story. Yeah, okay.
Any other question? If not, I think this